welcome. What we're going to be doing today is I'm going to be doing the physics of a bungee jump, because I know they can come up in paper one, in particular, along with SHM and material science and forces. And what I'm going to do today is I'm going to show how you can use SHM equations on a bungee jumper, but I'm also going to mention how important it is to understand how labelling is useful. So I've got this penguin here, and this penguin is going to be having a bungee jump, and the total distance that this the lowest from the bottom it gets is about 75 meters. Okay, so in a bungee jump, what actually happens is, of course, the person will jump off the side, has got a piece of elasticated rope, and they will go down, and then they will stretch, and then they basically will they won't go back to the top again, but they'll just oscillate around a point. So before I get into this question, I'm just going to move this over here. We've got a bungee jump here. We've got a height it goes to here. So at the top here, this object has got gravitational potential energy, GPE. And what happens is, as that thing comes down, there is a point up to here where there is no extension at all. The rope is at its length. So we're going to call this section A. So at A, your GPE is just getting converted. All you've got is GPE and kinetic energy here, because there's no extension of the rope. Okay, we're going to call this point here B. Okay, there. I'm going to call that B. What actually happens here, after this point, all the way up to point B, and I'm going to mention about point B in a few seconds here, is that it's stretching. Okay, so between this position here, you've got a bit of GPE, you've got kinetic energy, and plus you've got elastic. Okay, so as it comes down, it speeds up and speeds up, and then it gets to this point where it starts extending. Some of that kinetic energy is getting converted into gravitational and elastic. Kinetic energy is getting converted into elastic potential here. Okay, and you get to a point here where I'm not saying it is there, that you get to equilibrium. And this is where your kinetic energy is going to be the maximum, because your extension, F equals Kx equals mg. But the thing is just because you're equilibrium, you're moving at a constant velocity, which is why your kinetic energy is max, you're still moving. What will happen is you'll start to slow down, and you get to this point C. So C, after this, you keep on stretching and stretching until you get to C, where your GPE equals your elastic potential. So there is no kinetic energy here. So just to recap, when it goes down here, there is no extension. So the gravitational potential energy you're getting is being converted into kinetic energy here. So there's a mixture of GP and kinetic energy. And this is for the overall sort of length of the actual object. After you get to this point here, you start to extend until you get to your equilibrium point, where you've got GP kinetic, but at this equilibrium, kinetic energy is the maximum. And then you get down to this bottom where your GP and your GP equals your elastic. There's no kinetic because you're stopping. And in regards to SHM, if you remember, SHM is all about oscillations towards an equilibrium point. So this position here between the equilibrium point is the amplitude of the oscillation. This is why when a bungee jumper goes down, they will keep going, and they'll stretch to the bottom, and they won't go back to the top again. Because what actually happens is, after it's been extended, you've got elastic potential energy there. So some of that GPE has been permanently converted into elastic potential energy, and it will oscillate around that point. And of course, it will be a damped oscillation, because eventually friction gets involved and things like that. So it's actually quite important to realise just some of these things that I've labelled. So I've labelled that the bit before it extends is the length. This amplitude here, okay, is between the amplitude of the oscillation. So the difference between the equilibrium point and the bit where you've got GP equals elastic, so there's no kinetic, is your amplitude. And the total distance is the height. So let's actually go to a question over here that I'm just going to walk you through kind of those things I was going to say. So I've got an object here. So this penguin is going to be bungee jumping off a cliff, and the lowest they get is 75 meters. So the kind of questions that you'll be asked is little things like, one, what is the length of the rope? Two, what is the time period? Of the oscillation? Number three, what is the amplitude of the oscillation? And number four here, the max velocity and acceleration. Okay, so that's actually, so we've got 75 meters here. I'm going to have this penguin here weighing 100 kilograms, and this bungee cord that they're on has a spring constant of 250 newtons per meter. So, length of rope. So let's do this one here. So, got my 75 meters here. I've got this here, I've got my length here. And then it goes all the way to here. You get an equilibrium point here. And you have your bottom here. So this is actually quite useful to know all these sort of bits of information, that you know that at this point here, the GPE equals the elastic. Because you know that L plus this total extension, okay, is 75. So L plus the change in X is 75 meters. And this change in X is the change in the extension till the max. And at this point here, I know the GPE equals the elastic potential. So what we have here is I have GPE equals elastic. So I have mgh equals a half kx squared. So 100 times by 9.81 times by 75 equals a half times 250 times what, v squared. You end up as v, oh no, not v squared, I was getting carried away with myself, x squared, sorry. So I have got 100 times by 9.81 times by 75. So that's going to be 73575 equals a half 250 times by x squared. X squared equals, so times by 2 divided by 250. X squared is 588.6, and square root that, you get x. Let's bring this down a bit. You get x equals 24.26 meters. So I know that the total extension of this thing to cause at the bottom for all the gravitational potential to equal the elastic is 24.26. So 75 equals the length of the string plus 24.26. L is going to be 75. Take away that. That's going to be 50.74. There. So that is the length of my string there. So that was for question 1. So that was, what is the length of the rope? And this kind of question would be worth between 2 and 3 marks. 1, expecting you to understand the energy transformation. 2, for working out what the extension would be. And of course, 75 minus that answer would be that there. So let's go to the time period of this oscillation. So it is a spring system. So if you're going to be having a spring system, T equals 2 pi square root m over k. So T equals 2 pi root 100 over 250, and that equals 3.97 seconds there. Okay, so that's quite a nice one, probably be worth 1 mark. Okay, amplitude. Now I'm actually going to go back to this one, so I'm going to have it nearby. So I've got my amplitude here. Okay, so my amplitude of my oscillation, and I'm actually going to go quickly back to this drawing that I did up here. The amplitude is the distance from the equilibrium. All right, so we're actually going to use this thing here. So the first thing, I need to find the extension due to equilibrium. So that's F equals Kx equals mg. So 250 x equals 100 times by 9.81. Okay, so I've got 100 times by 9.81. So x equals 100 times by 9.81 divided by 250, and I get 3.924. So I know that to extend to get to equilibrium, I need to move 3.924 meters. But to extend to get to full extension, I actually extend a total of 24.26. So I know if I actually look at this here, if this here is, so if this was the length of my string, I know that to get to here is going to be 3.924 meters. So this is the equilibrium. I know to get to this position in total was 20.3, right there, 24.26. I know that this distance here is my amplitude. So if let's just zoom out a little bit. If I look at the total extension, that equals the equilibrium plus the amplitude. So I've got 24.26 equals 3.924 plus the amplitude. The amplitude is going to equal 20.336 meters. Okay, so this piece of string is going to oscillate with an amplitude of 20.366 this way down and 20.366 going up. Okay, so what's going to happen? It's not going to go back up to the top, but it will oscillate quite nicely around this point here. Okay, let's go into question 4, which was finding the maximum velocity. And here, so V max equals omega A, and A max equals omega squared A. Omega is going to be 2 pi F, or 2 pi over T. So having a look at this, I've got omega equals 2 pi over my time period, which was up here of 3.97. And that is going to be 1.58 rads per second. My amplitude, we go back here, I worked out was 20.336. And plug them in. So Vmax is 1.58 times by 20.336. And that is going to be, so 1.58 times by 20.336. And that's going to be 32.13 meters per second. And Amax is going to be 1.58 squared times by 20.336. And that's going to be 50.84 meters per second squared. And let's actually do some proof. Let's actually prove that those formulae actually make sense with the values you've got. So let's actually do the acceleration one first. So I'm going to prove that Amax, the maximum acceleration I'm going to get, is 50.84. So at the bottom, where I have a total extension of 24.26, okay, I have got an object with a tension going up and a weight going down. And that's going to be K delta X. And I'm going to have a resultant force going up, which is going to be the tension minus the weight. So it's going to be 250 times by 24.26 minus 100 times by 9.81. So 250 times by 24.26, which is 6,065. Take away 981. I end up with 5,084 newtons. And of course, that equals mass times acceleration. So 5,084 divided by 100, because that's the mass of my penguin, is 50.84. So as you can see here, I actually didn't have to work out the maximum acceleration. I didn't have to use VA max equals omega squared A. I could have just done some forces here. Okay, let's do another one. Let's work out the maximum kinetic. So the maximum kinetic energy is at this point here, where I've got this much extension and this much GPE. So let's have a little go here. So I have lost, so to go down to, so proving Vmax here to you. I know in total I've got 75. And I'm at this position here where I am past the length and I've got, so remember the maximum velocity is at the equilibrium point and the length of my string is 50.74. 74, okay, and this is going to be 3.924. So this to the equilibrium for 3.924. So this is the equilibrium. Okay, so I'm proving Vmax with this. So at the top of this, so at the top, the GPE I have is mgh. So that's a half, which is 100 times by 9.81 times by 75. So this is the total amount of energy that is in my system at any one point, times 9.81 times by 75. And that is going to be 73575. So 73575. So this is the amount of energy in my system at any one point. So at this position, at equilibrium, is where I have my maximum kinetic energy. And I have a little bit of GPE, plus a little bit of kinetic energy, plus here, I'll have some elastic too. So let's work out how much I've got. And I know, by the way, this is actually going to equal 73575 at this point. So GPE-wise, how far am I from the bottom? So 50.74 plus 3.924 is 54.664. 75 minus that answer, and I am 20.336 from the bottom, okay? Which kind of makes sense because if we look down here, my amplitude of my oscillation, of course, is from the bottom. So my GPE, mgh, plus a half mv squared, plus half kx squared. So mgh, I've got 100 times by 9.81 times by 20.336. So times by 9.81 times by 100, I get 19,949. Okay, so this here is the distance from the bottom. So distance from the bottom. Okay, plus a half mv squared. So I don't know what that is yet. So that's a half times 100. So 100 divided by half, so it's 50 v squared, plus a half kx squared. So it's going to be a half times 250, so 250 times 0.5, times by my extension squared, so times by 3.924 squared. And that's going to be 1924.7. And that again is going to equal 73575 there. So let's do some rearranging. I end up with plus 19,949. So I've got 21.21873 plus 50 v squared equals 73575. So 73575 minus that is, so 50 v squared equals, just move that up here, 50 v squared equals 51701. V squared divided by 50 is 1034. Square root it, you get 32.1 meters per second. So if we go and check that against our other answer, so I said, oh, hello, let's go up here. I said 32.13. Given the fact I was rounding, don't think that's bad at all. Okay, so here's some other proofs that you can actually do to actually prove Amax and Vmax. So you could actually do acceleration through forces, and of course you could do velocity over looking at energy formula. And it's all about knowing what is going on. So you understand that in a bungee jump kind of question, if I go up to the top of the penguin again, that at the top there's maximum gravitational potential energy that you have between this and before it starts stretching, you've got GP and KE. And then at B, when you're at equilibrium, your kinetic energy is the maximum, but you've got a mix of GPE, kinetic, and elastic. But at the bottom, you've got GPE and elastic only because it's stopped. Okay. So this is a kind of question, this will be quite a good exam question where they're assessing your ability to use SHM. But of course, as most exam questions, you'll find that you're allowed different routes of doing it. So for example, as you can see here, I did Vmax and Amax as omega A and omega squared A, but the examiner will not mark you down if you did it with forces or you did it with energy there. Okay, so hopefully that can help you guys with your energy using for bungee jumps, and take care.